So this video is a summary of all of the stuff that you need to know for rates of reaction at National 5. So in a chemical reaction, we need to know that the chemicals we start with are called reactants and the chemicals we finish with are called products. In the middle, we always have an arrow, and that arrow represents a transformation. So if we were reading out that equation in the orange box, we would say that the reactants change into the products, or the reactants turn into or become the products. Now, the reason we use an arrow that points in one direction is to show that we can only go from reactants to products and not from products to reactants. You need to know different signs of a chemical reaction so that you can identify that one has occurred. This is the list of all the different signs you need to know. Easy ones are colour change. You might also notice a solid forming from a solution. That is called precipitation. That is a sign of a reaction. If we notice an energy change, the reaction getting hotter or colder, that's a sign of a chemical reaction, and we have two words you need to know to describe those. A gas being produced, and you would identify that through fizzing, and odour, which is a smell being given off, and in some situations you might also see light being produced. Now, when it comes to those change in energy questions, or the signs of a chemical reaction, we have two key words. When a reaction heats up, it is producing heat and putting that energy out into the surroundings. We call a reaction that gets hotter or gives out energy or heat an exothermic reaction. You can remember exothermic is heat exiting the reaction, EX. The opposite is when a reaction becomes colder. Now, it's becoming colder because it is taking the energy out of its surroundings and the energy is entering into the reaction. That one is an endothermic reaction, where the heat is entering the solution and causing the surroundings to get colder. Now, when it comes to rates of reaction, we have an underlying theory called collision theory, and this explains what is causing a reaction to occur. Now, in order for a reaction to occur, your particles, your chemicals must collide. They must bump into one another. However, the majority of those collisions do not result in a reaction because the particles just collide and bump off each other. It is only whenever particles have enough energy during the collision can it be successful. And we call that minimum amount of energy the activation energy. Now, if we want to make a reaction go faster, we need to think about what can we do to the number or frequency of collisions and what can we do to the energy of the particles. So if we want to speed up a reaction, we can either do things which will increase the frequency of collisions. If we have more collisions happening, we will have more successful collisions. The second thing we can do is give particles more energy. If they have more energy, more of them will have this activation energy, and therefore more of the collisions that occur will be successful. Now, there are a few ways at National 5 that you need to be aware of for how you can change the rate of reaction. The first one is to decrease the particle size. Decreasing the particle size means taking a solid and breaking it into smaller pieces, or in the best situation, turning it into a powder. When you do this, there is more of the surface of the chemical exposed, and therefore there is more places for collisions to occur. So decreasing particle size will increase your frequency of collisions and increase the rate of reaction. The second thing we can do is increase concentration. Concentration means chemical dissolved in liquid. If we increase the concentration, it means we have more chemical dissolved in liquid. There's more particles in the same space. The particles are closer together, and therefore we will have more collisions happening, increasing the frequency of collisions. The third thing we can do is increase temperature, make the reaction hotter. When we do this, the particles have more energy and they move faster. If particles are moving faster, they're more likely to collide with one another. Additionally, because we've given the particles more energy by heating them up, more particles will have the activation energy. So temperature is really the best way. If we increase it, we increase our number of successful collisions and we give more particles the activation energy. And the fourth thing we can do is use something called a catalyst, which will automatically speed up a reaction. So you do need to know a definition of a catalyst. It is a question that frequently comes up. You need to know that catalysts are chemicals that speed up a rate of reaction but are not used up by the reaction. And you can say not being used up in another way, saying that they can be reused over and over. Now, how a catalyst works is that it lowers the activation energy, meaning that the particles need less energy to do the same reaction. You do not need to know this graph. You just need to know that catalysts speed up a reaction without being used up, and how they do it is by lowering the activation energy. There are two types of catalyst. One is called heterogeneous catalyst. Hetero means different, and this is when the catalyst is in a different physical state than the reactants. By physical state, we mean solid, liquid, or gas. So a heterogeneous catalyst would perhaps be a solid catalyst using liquid or gaseous reactants. The other type of catalyst is homogeneous catalyst, and homo means the same. So homogeneous catalyst is when the catalyst is in the same state as the reactants. So it could be a solid catalyst with solid reactants or a liquid catalyst with liquid reactants. Just remember, hetero means different, homo means same. Your spelling is not going to be marked on this. Now, when it comes to measuring the rate of reaction, the types of reaction you will be asked in National 5 always involve a gas being produced. And when it's a reaction with a gas being produced, there are two ways to measure the rate of reaction. One is to collect and measure the volume of gas being produced, or you can let the gas escape, and because gas does have weight to it, you can measure how the mass of reaction would decrease over time. So when it comes to collecting gases, there are two ways. In each of these methods, you need to be able to draw the bit on the right-hand side. So for each of these, you need to be able to draw this, or you need to be able to draw that, and you need to have labels on it. Okay? The easiest one is definitely the gas syringe. But you need a scale on the syringe so that you can measure it. If you're choosing to do the one on the left, the tube cannot have any blocks in it. So you can see here, the line for the water does not cross the tube. You also need the tube definitely pointing back up into the measuring cylinder. And like the gas syringe, the measuring cylinder needs a scale on it so that we can measure it. Rate always involves recording time as well as a quantity or a measurement. So you must also say or draw a clock or timer being used in your reaction as well. If it's the reaction that's producing gas, the second way is to let the gas escape and measure the mass lost. This is the experiment that you would be using for that. So you have your reaction sitting on top of a balance. You can put numbers on here to show that it is a mass balance, or you can just label it as being a mass balance. At the top of the reaction, you need a cotton wool plug drawn in there. Now, the reason the cotton wool is there is because gas can escape through the cotton wool, and as the gas escapes, the reaction will get less heavy. But if the reaction is bubbling, any liquid will be absorbed by the cotton wool and will not escape. So it means the cotton wool only allows you to measure the change in mass as a result of gas being lost. And like with your other reaction, when you're collecting the gas, you need to have a timer or a clock drawn because you need to always measure time as well as a quantity. Now, when it comes to calculating rate of reaction, the equation that you need to know is in the inside cover of your data booklet. It is rate of reaction equals delta quantity over delta time. That is how I would read out that equation. What the delta means is change in quantity over change in time. And that line means to divide. So you have your quantity divided by your time. You must write out that equation every time you're asked to calculate a rate of reaction at National 5. Always write it out. Now in the next few slides, I'm going to show you the 3 types of question you can get asked for how to calculate rate and how to get marks in each of them. So the simple calculating rates, you get given one quantity and one time. Now, whenever you're doing it, rate equals change in quantity divided by change in time. Now we don't have a change in time and we don't have a change in quantity. We just have one quantity and we have one time. We know the time because S is for seconds. So 20 is going on the bottom line. Our quantity is 60, so that's going on the top line. When we put that in our calculator, we get 3. Now, if this was a question, we have got 1 mark out of 2 because the second mark is for units. Now, when it comes to units, what we do is whatever our quantity was, we write out the units that were beside it, centimeters cubed. Then we do a forward slash, we look at the units for time and we do that. The alternative way of writing out units, and you will sometimes see units being written out this way, is your units for quantity, then your units for time without a forward slash, and instead you put a -1. It doesn't matter which one of these you use, that will get you your second mark. Okay? So 1 mark for doing the calculation and writing out the equation, 1 mark for units. Our second one is how to calculate rates from a table. When we're calculating rates from a table, you will always be given 2 times. So in this case, we've been asked to work out the rate of reaction between 10 and 20 minutes. Before I do anything, I am writing out my equation. Rate is change in quantity divided by change in time. Okay? Now, what I need to do is in the table work out which row is time and which row is quantity. Time is obviously the one called time, which means this other one here must be my quantity. Okay? Now, we were asked to look at 10 and 20 minutes. At each of these, we need the time and we need the quantity. Now remember, that means the triangle, the delta, means we're going to need to take away. Okay, now our two quantities are 1.2 and 2.2. Always take the small number away from the big number. So 2.2 minus 1.2. Okay, keep our line. Then we've got 2 times. We've got 10 and 20. Again, big number, take away small number. When we do that, keep our line in there. 2.2 minus 1.2 is 1.0. 20 minus 10 is 10. When we do that, that gets us 0.1 and use a calculator. When it comes to our units, we need to look at our table. Our time was in minutes, our quantity was in bar. So we write bar, because that's our units of quantity, / minutes, or bar minutes with a -1 beside the minutes. In this case, we get 1 mark for our units. We get 1 mark for selecting the right information from the table and 1 mark for showing that we do quantities divided by times. Okay? Our final one is calculating rates from a graph. And usually the way the question is asked is over the first 40 seconds or over the first number of seconds. Again, you've been asked to calculate the rate. So first thing you do, rate is change in quantity divided by change in time. Now the first 40 seconds means going from 0 to 40. So our time is going to be 40 seconds because that's how long it's taken us. Now our quantity, well, at 0 minutes, our volume of gas was 0. For our quantity, we need to go up here and then across. Now when we look across, we can see that from 70 to 80, there's 5 small boxes, which means we're going up in 2s. We are 1 box up, so that's 72. So it's going to be 72 divided by 40. I can't do that in my head, so I am definitely using a calculator. 72 divided by 40 is 1.8. Again, we need to do our units. In this case, quantity and time, those are our units. So it's centimeters cubed / seconds, centimeters cubed per second, or we can write centimeters cubed seconds minus 1. And again, it is 1 mark for units, 1 mark for selecting the right data, and 1 mark for doing your quantity divided by time. Now, when you get graphs, you're not just going to be asked to calculate rates. You might also be asked questions about when is the reaction at its fastest, at its slowest, when is the reaction stopped, and why is the reaction slowing down. So this slide explains that. Always, the reaction is fastest at time equal 0, right at the beginning, where you have all the reactants at their highest concentration. They are going to be reacting at their fastest. Now the graph begins to curve eventually. Now the reason for this is your reaction is slowing down. Why is it slowing down? The only answer you can give that is correct is the reactants are being used up. It is nothing to do with energy. Nothing at all to do with energy. The only reason a reaction slows down is because reactants are being used up. When a graph is flat or horizontal, it means it has stopped. And you can be asked for at what time does a reaction stop. Now what you do there is you look at your graph at where the line starts to be flat. You then look down to whatever time that was, and that is the point of the reaction stopping. So in this case, the reaction stopped at around 62 seconds. There's always a little bit of judgment as to when you think the graph became flat. So in questions relating to when the reaction stopped, there's always a range of answers you can give. The final thing in relating to graphs is being able to compare graphs. Now we have three graphs here, 1, 2, and 3. The rate is related to the steepness, not the height of a graph. So just because a graph is finishes at a lower height doesn't mean that it is a slower reaction. The steepness is how diagonal it is. So in these reactions, the speed, 1 is faster than 3, which is faster than 2. Okay, so we look at the very start where the reactions are fastest. 1 is the fastest, 3 is the second steepest, so it's second, and 2 is the most steep. You could be asked, what could have happened to turn graph 1 into graph 2? Well, we know we've slowed a reaction down. So 1 going to 2, what we could have done is increase our particle size, decrease our temperature, decrease our concentration, or remove the catalyst. In graph 3, if it's a lower height, that means less chemicals were used. Not a lower concentration or lower particle size, less chemicals in terms of mass. So if we think reactions 1 and 2, if they used 2 grams of solid, graph 3 is about half the height, so it might have used 1 gram of solid. That's the only reason the height or the finishing height of a graph would change, is if you had less chemicals. Okay, so remember, the steepness, how diagonal it is, you look at the start of the graph, whichever one is steeper is the fastest one. It has nothing to do with the height. If you're going from a faster reaction, a steeper one, to a less steep one, you have to think about what are the factors that could have caused a reaction to be slower. Or if you're going from less steep to more steep, what could have caused a reaction to go faster? If a reaction finishes at the same height, it must have the same mass of chemicals going in. If it finishes at a lower height, it must have less mass or fewer chemicals going in. So that has been our summary. I know it's like 24-25 minute video, but that covers everything you need to know about rates of reaction with worked examples.